All right, guys, this is Unit 12.1, the last unit on nuclear chemistry. All right, let's begin this nuclear unit with some information about what exactly nuclear chemistry is. Now, nuclear chemistry is the study of the nucleus of the atom, and we're going to do this really, really quick in 3 or 4 days of you listening to me on the videos, but we have to talk about some vocabulary first. So the first word that I want to talk about is something called radioisotope. Radioisotopes, or radioactive isotopes, also shortened isotopes, shortened to radioisotopes, are substances that are radioactive. And what does that mean? Well, we all go, oh, radioactive, it's dangerous. Yes, there are some radioactive substances that are dangerous, but there are some that are very helpful to us too, with the treatment of cancer, or to diagnose a cavity, or to tell you if you broke a bone in your hand if you go to the doctor. All right, so what is a radioactive isotope? Radioactive isotopes are isotopes that their nucleus, nuclear chemistry, are not stable. Okay, I'm going to draw a stable one on the board here. Let's draw carbon-12, and let's talk a little bit in review about what these numbers mean. This helps you with review, and this is why we keep this unit for the end. All right, this bottom number down here is the number of protons. It is the atomic number. It is also the nuclear charge. Oh, it's all coming back to you now. Okay, so it's those three things. This top number is the mass number. It is also the protons and the neutrons combined. When the protons to neutrons ratio is 1:1, then it is a stable nucleus. Well, in this case, let's see if I can make this a little smaller. There we go. In this case, the number of protons in that carbon-12 is 6 protons, and we got that from here. And the number of neutrons in this is 6. So we have a 1:1 proton to neutron ratio. Carbon-12 is a stable radioactive isotope. Well, it's not radioactive. Sorry, scratch that. It's a stable isotope. Okay, now if we look at carbon-14, okay, we've got 6 protons, but we have 8 neutrons. And so this gives us a ratio of 3:4. Okay, I just reduced that 6 to 8 to 3 to 4. And that is not a 1:1 ratio, so we consider this a radioactive isotope. Okay, when the proton to neutron ratio is close to 1:1, we say that it is in what we call the band of stability. So I went ahead and I grabbed a picture of the band of stability, or they call it the belt of stability. So let's take a look right here, belt of stability, and that's this area that I'm highlighting in blue. If the proton to neutron ratio falls within that band, we say that it is a stable isotope. If it falls above this line right here, or below this line right here, and you're not in this band that's here, then we are considered a radioactive isotope. We are not stable. Okay? I'm not going to go into that any further except to say that as you're down closer to the lower number of protons, like hydrogen, helium, lithium, beryllium, and those guys, the proton to neutron ratio is 1:1 right here. See how it hits 10 and 10 and 20 and 20? Okay? And then it starts to veer off just a little bit, and your ratio gets a little bit off. Okay? Because now when you're in, you can't see where I'm pointing, but if you're in here, in this band, it's not 1:1. This line is on the 1:1. That line right there. This line, okay, is not on a 1:1. It's the number of neutrons is twice the number of protons. That's up here, okay? And here we're at 1:1. If you're in between them, you're considered fairly stable isotope. As you get heavier, as the number of protons, like uranium, 239, and it has 92 protons, that is not a 1-to-1 ratio. So uranium is considered a radioactive isotope. Radioisotope. Okay, I'm going to take a second to just talk about the 3 I words as a little bit of a review. Since I'm not there when you're listening to this, I want you to go over those 3 I words. Isotope, isomer, and ion are the 3 I words. So let's do that on the next page real quick. Okay, so we had ion back in the beginning of the year. That's a charged particle, and it's made when you gain or lose electrons. Then we had isotope, which is what we're talking about here. Okay, isotopes are same atomic number, different atomic mass. And then the last unit, when we did organic, we talked about isomers. And isomers were same molecular formula and different structural formula. Okay, so these are the 3 I words. Take that for a review. Make sure that you know them. Now let's get back to our nuclear. Okay, so we've defined what a radioisotope is. A radioisotope is not stable in the nucleus, and it doesn't fall in that band of stability. Now, we also have another word I want to mention, and that word is transmutation. Transmutation. Okay, trans is to change, and mutate. Transmutation. Okay, now we are going to change an unstable isotope into a stable isotope. How are we going to do that? We have to change the proton to neutron ratio. And now there's 2 ways to do this. There's something called natural transmutation and artificial transmutation. We're going to start with the natural transmutations. Natural transmutations are not man-made. They happen in nature. And there's a couple different ones. We're going to start with, let's take a look at table O for a second. Let me go grab one. Existing video. Here we go, table O. And we have on table O, I don't know if you remember this, but we had alpha particles, beta particles, gamma rays, neutrons, protons, and positrons. An alpha particle we saw when we did Big Ernest Rutherford gold foil experiment. And a alpha particle has a mass of 4 and a charge of +2. We're going to use that when we do natural transmutations. Beta particles, also known as electrons, have a mass of 0 and a charge of -1. Gamma rays have no mass, no charge. Neutrons have a mass of 1, no charge. Protons have a mass of 1 and a charge of +1. And finally, positrons are positive electrons, and they have a mass of 0 and a charge of +1. Okay, so keep this in mind, this table O, as we go through this. The first type of natural transmutation, let me write that for you, transmutation, is called alpha decay. Okay, alpha decay means that the nucleus of the unstable radioactive isotope is giving off an alpha particle. So I went ahead and I grabbed table N in your reference tables, And I want you to take a look right here where it says decay mode. That decay mode is telling us what the nucleus of the atom is going to give off. So we're going to look at francium-220 right here, and you see that this decay mode is an alpha symbol. That means that francium-220 gives off an alpha particle. Okay, I'm going to draw it over here for you so you can see. Let's say we have a hunk of francium-220. If the francium-220 gives off an alpha particle, let's say this red section is the alpha particle, when it is done, it is going to be something else that is smaller. That's where the hunk came out of, right there. And it's going to be the red piece that came out. Okay? It broke down, francium-220 broke down into this, whatever it is, and this alpha particle. Now, an alpha particle, again, is a helium nucleus. So I'm going to write it as a helium nucleus. 4/2He. Okay? What was left when this francium-220 gave off that alpha particle? Let me see if I can find a pointer. I never can remember where anything is. Okay, so this francium-220 transmutated into something and an alpha particle. Okay, it started out with a mass of 220. It changed, that's the arrow here, into something and something else that has a mass of 4. So this $220, and it changed into something plus $4. Well, if you're saying to yourself, law of conservation says if I start with 220 and I end up with 4 and something else, that something else had better be 216. You see how these two numbers add up to this number? Always make sure that your masses, you have conservation of mass, right? You start with 220. If you decay and become an alpha particle, then whatever is missing has to have the mass of what's remaining. All right, now down here, we have number of protons. They didn't tell us what francium's number of protons is, but we can look that up. And when we look at our reference table in the bottom left-hand corner for francium, you're going to see atomic number 87. Well, if we start out with 87 protons, and the nucleus of that francium gave off an alpha particle that has 2 protons, or atomic charge of +2, right here, right there, that 87 has to equal a number plus 2. And so that number has to be 85. So we have transmutated from something that has an atomic number of 87 into something that has an atomic number of 85. Now, when we look at our periodic tables, we're going to see that atomic number 85 has a symbol of At. And we can fill that in. Okay? So we have changed the francium-220 into, by giving off an alpha particle, we have changed it into At. That is alpha decay. You're going to recognize natural transmutations because they will always start with one reactant and they will become 2 products. One of the products is going to be an alpha particle, a beta particle, a gamma ray. One of those 2 products is going to be, in this case, an alpha. And because it's an alpha, we call it alpha decay. Now let's look at one that is going to break down, but this time it's going to emit or give off a beta particle. So I'll get a highlighter here. And beta particles are always illustrated with this little b with a minus sign. Okay, so let's take this cobalt-60. We'll take this one right here. That's the one I'm picking. I could pick any one, but I picked that one. So we're going to start with cobalt-60. Cobalt, atomic mass of 60, and I got that from right here. Okay, it is going to give off a beta particle. Now the beta particle has an atomic mass of 0. It's an electron, no mass, and has a charge of -1. And it's going to end up breaking, that cobalt-60 is going to end up breaking into this beta particle and something else. Once again, we are starting with one reactant and we are ending with two products. That's important when you're picking out natural transmutation. You start with one reactant and you end up with two products. Well, let's figure out what this product is going to be. Well, we start with a mass of 60 and we break down. This has no mass, so we're going to do 0 plus what number is going to give us 60. And hopefully you said 60, okay? Because the law of conservation of mass, if we start with 60 and we break down into 0 and another number, that number better be 60. Now we have to look at the atomic number of cobalt. Cobalt is 27. I just checked my reference table, so that's 27. Okay, now we're going to take 27 as its atomic charge, or its nuclear charge, I should say, and this has a charge of -1. Be careful with this. These two numbers, these two bottom numbers, have to add to 27. What number plus -1 gives you 27? And I know you're all yelling, it's 28, it's 28. Good. So 28. Now we're going to look at our reference table again. I have to go over here and look at it. And atomic number 28 is going to equal nickel. So cobalt-60 undergoes natural transmutation. It emits a beta particle. And when it transmutates and it changes into nickel-60, which is an isotope that is more stable than cobalt-60. It transmutated into a totally new substance. So I'll just write this down here. Oh, where'd my pen go? Okay. This is called beta decay because we are giving off a beta particle. All right, and the last type of natural transmutation that I'm going to draw out for you is called positron emission. And it works exactly the same way. Positron emission. It's natural transmutation. And we're going to find a positron emission. Let's zoom in here. Let's do potassium-37. You see how it has a little B with a plus sign? Look back at table O. You'll see that B with a little plus sign is a positron. Okay, so we're going to take potassium-37. We're going to take it. We're going to break it down into a beta particle. Not a beta particle, a positron, and something else. Again, take note that this potassium, there's one reactant and there's two products. That's the key when they ask you which of the following is natural transmutation. If you start with one thing and you end with two things, then you have natural transmutation. Okay? Also, you're going to have numbers written for your atomic masses and your atomic numbers. So we'll go ahead and we're going to fill in the atomic number for potassium, which is 19. You get that right from your reference table. And now we can figure out what goes here, right here in this green square. And they love to ask you to fill in the green square. So we've got 37, the arrow, 0 plus what number? Well, hopefully you're saying 37, 37. So 37 goes on top. And the bottom number is 19 because its atomic nuclear charge is 19. Here we have a +1. And what number is going to go here? Well, what number plus +1? What number plus +1 gives you 19? 18, 18. Good. 18. So we're going to fill in an 18 here. Then we're going to go over to our reference tables. We're going to look up what element is 18, and this is Ar, which is argon. And so when potassium-37 naturally transmutates by giving off a positron, this is the positron, and I knew that from here, okay, it will change to a more stable isotope, argon-37. All right, I tried to copy and paste this as best I could. It's a little bit blurry, but it's on your Google Classroom. I want to make sure that you all have this written down in your notes. Okay, the first part of nuclear chemistry, we talked about the different types of particles that are emitted in radioactive isotopes. Alpha particles have the heaviest mass. Well, they also, I didn't mention this before, but I'm going to mention it right now, have the least penetrating power. It should make sense because if you have a bigger mass, if let's say I took a bowling ball and I threw it at the wall as hard as I can, it's got the biggest mass, it's got a very big mass, it's a bowling ball. I might get it to dent the wall, but I probably won't get it to go through the wall. So alpha particles have very low penetrating power. They don't generally penetrate things like even a piece of paper. They have trouble going through that piece of paper. You can block them very easily. Beta particles have no mass, so they tend to go through walls or skin, anything to that effect. So they do have greater penetrating power. Gamma particles, they're way down here, have no mass and no charge. They also have the greatest penetrating power. They can go through pretty much anything. Okay? So alpha particles have the least penetrating power. Gamma rays have the most penetrating power. Over here, we talk about particle acceleration. The bigger you are, of course, the harder it is for you to accelerate. We can accelerate a particle with a magnetic field. If I take a box and put a charged field, positives on top, that's positives, and negatives on the bottom, and out of this box comes an alpha particle. Well, alpha particles are positively charged. Whoops, I circled the wrong number. Positively charged. They're going to go towards the negative plate of the accelerator. And depending on how negatively charged this is, how fast we can get those particles to move. And then if we have a beta particle, which is negatively charged, it's going to go towards the positive plate. It's hard for you to see what I just drew there. Those are little B negatives. That's better. Come on, Kaufman, get it together. Okay? Negative charge is going to go towards the positive. If we have a gamma ray with no mass, no charge, those are kind of going to go straight through. That's kind of like a funky looking Y thing. Okay? No mass, no charge. They're not deflected by particle accelerators. And that's why it says neutrons and gamma particles do not work in particle accelerators. You can't direct them where you want them to go because they have no mass and no charge. All right, so that pretty much wraps up what is radioactivity and natural transmutation. In the next video that I'm going to make, we'll talk about artificial transmutation. Then in the third video, we'll do some half-life stuff. And in the fourth video, if I get that far, we'll talk about benefits and risks of radioactive isotopes.